Hello and welcome to the Open Systems Media IoT panel discussion, Scaling IoT Applications Part 2, Industry Examples and Architecture. I'm Kurt Schwader, your moderator, with today's speakers Josh Peterson with Ayla, Bridget Carlin from Intel, Stephen Graves from McObject, James Kirkland from Red Hat, and Brett Murphy from RTI. Today's schedule consists of about 50 minutes of presentation material, leaving about 10 minutes at the end of the hour for audience Q&A. Before we begin, I'd like to run down some important features of your viewing console. First is the Enlarge Slides button. This button will maximize the slides to fill your entire screen. The Download Slides button allows you to download and print the slides if you'd like a hard copy to follow along with. The button labeled Forward to a Friend enables you to send an email to someone that will include a registration link to this eCast so they can also attend. The Ask a Question text box enables you to participate today. You can simply type your question into the box and submit it using the Submit button. We encourage you to submit questions at any time during the panel. We encourage you to do so early and often while you're looking at the material and the questions fresh in your mind. We'll address as many of these as we can during the closing Q&A. If you have a question pertaining to the eCast operation itself, you could submit those too, and one of our technicians will be happy to respond to you during the eCast. This and all Open Systems Media eCasts are copyrighted and may not be used in any way without the express written consent of Open Systems Media. We have an all-star lineup of IoT panelists returning with us today for Part 2. Josh Peterson is a Director of Product at Ayla Networks. He has a long and successful track record with product development for platform as a service, software as a service, and mobile environments, making him a very valuable asset in the IoT space. Bridget Carlin is the Managing Director, Internet of Things Group at Intel. She brings a wealth of experience to the panel in a variety of industry verticals, leveraging silicon, software, and services from IoT edge to cloud platforms. Stephen Graves is the President, CEO, and co-founder of McObject. Stephen is a persistent storage and embedded database expert. He complements these skills with far-reaching background in embedded and real-time programming as applied to IoT. James Kirkland is Chief Architect of the Internet of Things and Intelligent Systems at Red Hat. James has a depth of experience in Linux and Unix, has significant experience in IoT solutions in the transportation and energy sectors. Brett Murphy is the Director of Business Development at RTI, the Industrial Internet Things Connectivity Platform Company. Brett has a long and successful history with software and system development across a variety of industries with specific expertise in embedded software, network middleware, and scientific computing. Welcome, panelists. It's time to get right into our first topic, IoT Industry Panelist Choice. We did something kind of new with the panel today, and we gave a panelist a chance to pick an industry, then discuss the kinds of IoT applications and systems that are being considered, under development, or being prototyped, or deployed in a limited or full scale. We wanted them to pick a quick functional description, a general architecture, and some deployment goals. We'll start off with Josh. Josh.
Thanks, Kurt. Today we're going to talk about a connected smart sock used by one of the Ayla customers that allows parents to basically proactively monitor the health of their sleeping infants. This is called Owlet Baby Monitor. This is basically a really small sock that you fit on your sleeping infant. What it does, it allows tracking of the child's heart rate, oxygen levels, and skin temperature in real time, transmitting that back to the parent to understand how their baby is doing to monitor during their sleep. Now, some of the key features of this that are really specific to IoT is basically enabling these parents to access live vitals anytime, anywhere, via wireless base station access and then push up to the cloud. Now, when we talk about IoT application, Owlet came to Ayla as sort of their cloud connection part of this, right? Ayla has an IoT platform. So what they needed to do was get the data off of this device that gets stored on a local base station up to the cloud. Okay, this is sort of the bread and butter of Ayla Cloud. But what happens is then that data is captured, tracked, analyzed in Ayla Cloud, but Owlet wants to do something with it on their own, right? These devices are transmitting data constantly. They're constantly streaming, creating large files, large log files of data, right? So the challenge here with an IoT application was to be able to move these device logs of data off of the Ayla platform, transmit it over to the Owlet platform for their own offline uses, okay? So really what we're talking about today in terms of an IoT application is solving basically a low latency cloud-to-cloud data exchange, right? Devices push data to a cloud, that's the IoT platform, that data might need to go somewhere else. So the first couple use cases we're looking at is being able to enable a data stream where we can move this data safely, securely, with low latency from the ALA cloud to the Owlet cloud, okay? But then the second part is to be able to understand, transmit data when there is some kind of device issue. So there's the bulk data movement. There's also identification of a device error that can be sent to the Owlet support team to be able to jump in and proactively support that device. Now, the architecture for this is kind of a common web standard thing where we're talking about web sockets. We're talking about two cloud-to-cloud or two clouds connecting to each other via web sockets, okay? We have subscriptions, basically data streams, that the Owlet team creates a DFS client to call back to the ALA cloud using stream keys for authentication. They're then able to, at their behest, pull this data over from ALA and make use of it for their own online or offline analysis. So with that, I'll pass the ball on.
Great. Thanks a lot, Josh. Bridget.
Hi. Okay, great. Thanks so much. So what I wanted to focus on today is very specifically the industrial IoT. It's a really big segment of the overall Internet of Things. It's expected to be about a $151 billion market by 2020. And at Intel, we sort of look at industrial as covering manufacturing, energy, smart buildings, smart factories. And we know that globally this is a very important initiative. You may be familiar with initiatives like Industry 4.0 that kicked off in Germany and frankly across the EU, as well as China, and their publicly stated objective of creating an entirely intelligent manufacturing ecosystem by 2025. So the use case I wanted to talk about today, actually wanted to cover two things. One is in terms of the use case around predictive maintenance. When we talk about getting engaged with IoT, one of the biggest questions is what's the clear ROI, or essentially, how do I cost justify investing and embarking on IoT? So we found that predictive maintenance is in the top 5. And then the second one is around inventory and asset tracking and management. This is another one that when we span the areas of industrial IoT, this is something that translates to a number of different vertical segments. So to kind of just to kick this off, I wanted to give you 2 examples. One is with Fujitsu, who not only is a partner but also a customer, and their challenge around manufacturing notebook PCs. The challenge there is around the costly repair process. And so essentially what we're going to examine here is the challenge of connecting existing internal process machinery, a variety of different sensors with different data formats and protocols, and being able to ingest that data and essentially get to a predictive maintenance scenario where ultimately they would be able to know before the manufacturing line went down that there was a faulty part and where that part was. And the second aspect, I want to touch on a very broad industry-wide problem, and that is the challenge of inventory stockouts and overstocks. And so I want to talk a little bit about Levi's and how that addressing, which is frankly about a $1 trillion annual problem for the retail industry, and that is around how to manage in-store inventory and get to a level of improved accuracy, which today is at best about 65% inventory accuracy. And what we'll dive into a little bit today is around how to use existing RFID tags that are already sewn into the jeans and the clothes you may see in the store, and then how to deploy RFID readers at the store level, ingest that data, be able to analyze it at the edge in real time, and then be able to send that data to the back end and integrate with the inventory system at the back end level to be able to update and improve inventory tracking, not only at the store but for the store-wide data.
Okay, great. Thanks, Bridget. We have a consumer kind of application and a retail kind of application here. That's great. Steve, what have you got for us?
Yeah, Carl, thanks. And thanks to Bridget for sizing up the opportunity in the industrial Internet of Things. We've got customers spread all around the industrial Internet of Things, for example, in smart grid, smart buildings, smart cities, and industrial control, also various consumer devices. We're best known as a solution for the things side of the Internet of Things and less known for the server and the cloud and the analytics side. But we've enjoyed success in big data or fast data world of financial markets. So ExtremeDB's ability to scale is also well documented. We have a cluster of customers with various applications in railway systems. So that's going to be the industry that I'm going to use to illustrate scaling concerns vis-a-vis database management systems for the industrial Internet of Things. The first customer implements tracking systems for safety. They chose a safety-certified RTOS and the Ada programming language for those reasons. They create an in-memory database that's populated on startup with data that they extract from SQL Server and then is updated with real-time local data. While it's an in-memory database, they employ transaction logging for recovery and high availability for continuous operation. Again, it's a safety-critical system, so high availability is a necessity. The system utilizes wayside monitors to collect safety-related data, such as acoustic monitors for detecting bearing problems, temperature sensors, for example, for stuck brakes and brake wear, and also RFID and photos to tie the collected data back to the particular car. The second customer develops supervisory and control systems on the train, including high-voltage insulation, fire suppression systems, closed-circuit TV, power SCADA, air conditioning, and running gear malfunction. The functions incorporate forecasting and trend analysis for the scheduling and preventative maintenance. The legacy systems perform these functions in the control center against batch-uploaded data. This particular initiative is to move those functions to the train and in real time. So this is an example of edge computing, in other words, moving the intelligence out from the cloud or the fog to the very edge. The data is still uploaded to the control center, though, so that those system-wide trend analysis can be conducted, including human factors. For example, a number of engineers that are all mishandling the same piece of equipment in the same way on different trains. Yet another customer implements a freight traffic control and dispatch application. A server-side supervisory application collects real-time data, again from rail wayside inspection devices that reflect the state of various wayside objects, for example, semaphores, tracks, and so on. These are collectively called generically resources. That state information is then used for identifying locations and scheduling and monitoring train movements. Train scheduling is done in the context of a different server-side application. The database is used for keeping resource data, again, semaphores, tracks, etc., and communicating the resources states to the train scheduling application. Further, the resource manager database is utilized for creating network communication messages that are sent to dispatch stations, and then those dispatch stations control train movements over a certain geographic region, which is very similar to air traffic controllers that pass aircraft to one another as they move along their routes. And then the last example that I'll cite was for a new architectural concept, specifically pull instead of push for message routing to handle traffic between wayside devices, locomotives, and back office applications. So whereas the first three examples were all edge systems, this is a server that's receiving data from edge devices. And the routing table is realized in an ExtremeDB in-memory databases. The messages are put into the routing table, and the optimal route is then identified based on a number of routing rules and the current network configuration that's stored in the database as well. Routing rules consider factors such as the time to live for the message and the priority of the message. And like the other safety-critical system, the router is required to be highly available, and they achieve that by employing ExtremeDB high availability implemented over a Solace messaging device. So the Solace messaging device makes sure that those messages themselves are persistent. Back to you, Kurt.
Okay, great. Thanks a lot. So railway and the database kind of paradigm within that. James, what have you brought to the panel today?
So we'll be talking about smart cities and how that interfaces with smart grid and smart transportation. We've had a lot of experiences with helping customers to build secure operating environments, and then on top of that, being able to move the data to the right point at the right time and in the right format to be able to make decisions and smart decisions. So it's all about the data flow and data movement. So we've got examples where we have helped customers build, for example, people counter solutions into transit, where they're able to keep track of the flow of passengers on and off of different buses, different types of transit, things like that, fare box management, but also provide services at the same time on the bus or tram or whatever it is by using the same infrastructure. So for preventative maintenance, for digital signage, for providing internet access for the consumer that rides on the transit, so that you're able to make the most use of it. Also with smart grid, being able to make the most of the bandwidth that's available and try to minimize costs. So using gateways in that case to only transmit the amount of data that you need to transmit over the wire versus transmitting everything. So either batching of data, summarization of data, things like that. And then we've got experience as well in cities like Valencia with smart parking, where essentially a messaging-oriented architecture. Again, you're able to go ahead and use that core infrastructure to monitor state of things, to advertise when there's availability for assets and resources. So generally you have a series of availability services, whether service is available or not, where it is available. It's maintained using business rules, messaging, and lightweight ESB that come from Red Hat, so that you're able to maintain these core services. And then what you have is, once the data is made available publicly, people are able to build new services on top of it. So, for example, looking at foot traffic and street traffic and having that be taken by third parties, and being able to build that into a model for the cost of retail real estate by determining the foot traffic and car traffic past certain points and locations.
Okay, great. So from railway to smart cities, Brett, what do you have for us?
Thanks, Kurt. I'd like to talk about a specific example in healthcare. GE Healthcare, their Light Care Solutions unit, develops devices and solutions for monitoring patients, typically in hospital and also in the home, and often with a lot of real-time data, like James was saying, that needs to be shared across the system. For example, an intensive care unit, an ICU might have dozens of devices or a couple dozen of devices for a patient. And if you look at those devices in a picture right now, current state of art is that each device has its own front end with some sort of data presentation, maybe a audio alarm, and none of it's integrated. And the way it's integrated is a nurse or a doctor or technician runs from device to device trying to figure out what they're all saying, figuring out if it's a false alarm going off. There's no real integration there. So that's a big challenge. Another challenge is chronic disease is rapidly rising, and things like diabetes, hypertension, obesity. And so there's a need to monitor and gather information from these patients in their home for the purpose of prevention, treatment improvements, and management of the disease. Of course, you want that information that's coming from the home devices to get integrated with the in-hospital information when a patient comes in for a checkup or they have some sort of acute episode treatment, some sort of emergency. So GE Healthcare is developing a next generation architecture using industrial IoT protocols and architectures. So they're in-hospital devices. They're making more intelligent, as well as, of course, connecting them up via the network. And then there will, of course, be a connection of the information flowing out of the patient rooms, the medical devices, and the hospitals to a back-end information center. And that, in turn, will be connected to devices that are monitoring people in their homes. So this architecture all has to be highly performant. It has to scale to hundreds of thousands of devices, maybe across a single healthcare provider system in multiple hospitals, as well as be secure and ensure patient data privacy. Thanks.
Okay, great. Thanks a lot, Brett. Great mix of from consumer to retail / industrial and to railway, smart cities, and healthcare. Let's talk about scaling and drilling down on the scaling factors. So for each panelist in these industry and applications that you've introduced, I'd like you to describe the scaling considerations. For example, is the scaling by users or geographical reach, maybe number of sensor inputs, or like Brett was saying with the medical devices themselves and the interoperability there. System upgrades, that's a consideration. How do you deal with upgrading the system software or the feature set? What security holes result as things scale? Lots of times people can self-contain things in a prototype, but when you start scaling, security holes start existing. So Brett, what are the important scaling factors for medical, and what kinds of solutions are there?
Sure, Kurt. So as I was talking about with GE's system for their patient monitoring, they are developing a digital health architecture, as they call it. And this has to scale from anywhere from like 1 or 2 devices, maybe in the home or in a simple in-hospital situation, up to something like 200,000 devices across the hospitals and the homes for a single healthcare provider system. Each patient in the hospital these days, if they're in there for acute care and they have medical devices connected to them, right now the average is about 1.5 gigabytes per day, and of course can go much higher depending on how many devices and the amount of info they're putting out. So when you scale this across dozens to hundreds of patients and multiple hospitals, you have quite a data sharing and data connectivity challenge. Also, performance is critical as the data is real time. And so typically there's going to be some sort of local processing, potentially local storage, and analysis going on. And this could be at different points in the system. So the data has to get moved around in real time and stored and analyzed. You might be bringing data up from a particular patient and then connecting that with historical data in the back end information processing center with in-home information that was already gathered. And security is another scaling challenge in the system. Each device has to be authorized and the data it's generating assigned to a particular patient. So you can imagine that a patient comes into room number 1. There's some medical device in there, number 111. So you've got patient X showing up. Now medical device 111 is attached to patient X. And so the data coming out of that medical device belongs to that patient. So the system has to identify that, ensure the privacy of that data, because the patient has privacy rights with respect to that data. So that all has to be managed. And this has to be done across a system where the patients move from room to room, a device fails and has to be replaced. All of that security, all that management, and all that monitoring is also a massive scaling challenge.
All right, interesting. Great. Josh, with respect to your consumer and infant monitoring device, what are the scaling factors?
It's interesting because as Brett says, this is kind of a healthcare-related thing, and while as a consumer device, everybody hopes that it takes off like wildfire in the market and units just start flying off the shelves. But you just don't know, right, because it's up to the consumers. So the scaling factors in this use case, they're not so much the massive volume that we would expect. It's more of spikes, right? And a good example is actually the real story with Owlet was this product launched, had some success, even saved the lives of a few children. So what happened? Social media news got out, and all of a sudden these things did start flying off the shelves, right? Which is what these guys want, was what we want, right? But this is where the scaling factor came in here, is that being able to get the data over to the Owlet team in an expedient fashion so they can support these customer devices, right? And so, again, as these devices collate the data in the log files and send them over, basically almost every 20 minutes or so. Now, so the goal then became, how do we maintain this data stream, right? The latency between device to the cloud, we have that handled, but then getting that data over to the support team so that if somebody reports a problem with their unit, these guys can get on it really quickly because, again, social media made them successful because that's marketing today, but also it's harmful. And if they're not really attentive to the needs of their consumer base, it can be harmful for them, right? So the ability to get this data over to them really quickly so they can act on it is key, right? So what we do then on the platform is to be able to enable what we call buffering, right, to buffer the data. And so this is based on our insurance against data loss. So basically as the data builds up and the demand grows, we're able to basically let it out at a pace that works for them. And if something happens, we're able to then replay back and get them the data that may have been lost, and they could still support their devices, okay? Now, the scaling factors then focus around the ability for the buffer to handle spikes, okay? I'll kind of say this again, is let's say Oprah Winfrey tweets about the Owlet baby sock. What happens? They sell 10,000 units overnight, right? That's a massive spike that this buffer and this system needs to be able to handle, okay? But then also once these active data streams are enabled, being able to maintain them, right? Because, as you know, this is a network type thing, and network connections go down for the darndest reasons at the darndest times, right? So we need to be able to address the challenge of stream maintenance, right? The connections go down, stream keys can be closed accidentally or lost. We need to prevent against that, prevent against the data loss. But then also that number of devices is a challenge as well, right? So in the buffer, be able to enable or handle new events, net new, that giant spike, but also be able to replay past events that may have been lost in transmission or lost on the receiving end, okay?
Great. Yeah, that's an interesting point in scaling factors for consumer and the impact of social media and communications on how and when things scale. Bridget.
Yeah, sure. So kind of just let's focus a little bit, let's pick up on retail. And I mentioned about the Levi's use case and using RFID in the store. So some scaling challenges when we think about moving from a POC or a pilot to really scale out so that Levi's can take advantage of some of the optimization and opportunities with IoT. So when we think about inventory accuracy, there are a number of challenges, right? Ultimately, Levi's and most retailers are trying to get to a responsive retail environment. They want to be able to have the right size, the right color, the right item on the right shelf, in the right store, when the consumer comes in. And they have an outside dynamic of what happens with online retail as well. So there's a couple of vectors of concern. One is making sure that the data is accurate and matches with the physical world, and then being able to ingest multiple types of data, not only what's happening in the store and potentially in the warehouse, but then also what are the dynamics happening online and how does that impact a retail, brick and mortar store. So in this scenario, one of the challenges with ultimately getting to improved inventory accuracy is being able to understand item movement, misplaced items, item replenishment, item identification. As an item may move from the warehouse to the store to the dressing room, then back on the shelf, and that sort of thing. So just tracking the data on a real-time basis ended up involving a number of different inputs. It's not just what the RFID tags were reading, but what the other information from other sources like the warehouse and also mapping to what the inventory system had identified. So that sort of was one of the key areas when we thought about scaling beyond a POC, a proof of concept or pilot, was understanding just all the different sources of data that would need to be ingested, how they were going to be aggregated and analyzed to give the real-time assistance that was needed at the store level. The other thing I think that's useful to point out is that, when you go into an environment, you're going into an existing environment, and there is a degree of awareness and consideration. There's going to be POS systems. There's going to be some sort of inventory tracking that the clerks are doing. And being able to now augment that set of automation or whatever is already in place in the store and being able to integrate it with other types of data. So one of the challenges that I think as a broader industry that we faced is that there was this notion of being able to integrate the new apps, the new data with existing hardware and software, and how that integration was going to work. So, fitting in, most retailers and so forth have some level of app inventory management and so forth. So we needed to consider the software integration and the data integration at that level. The other area was around interoperability of devices and being able to, not just with RFID, but being able to ingest data from different formats and protocols and being able to ingest that. And then, as I think each of us are identifying, is you can't have a conversation about IoT without bringing up security, right? And so one of the issues was around as we started bringing in other sources of data and integrating it, how secure was the source and how much could we trust that data. So we had the challenge of understanding what points were actually already secured and where were our gaps and where do we need to go insert security. And we found that for the Levi's implementation, we used the Intel IoT Gateway, which comes with pre-integrated security using McAfee at the gateway level. So irrespective of as the data came in through an RFID source or a POS system or what have you, we were able at the point of, as it was ingested in the gateway, to secure it at that point. And then from the gateway edge back into the cloud, we created a secure loop, if you will, for that data. And so it was a more of a trusted data. And the one other thing I wanted to mention is that, I talked about coming into an existing environment. One of the challenges that we all have is being able to have an end-to-end architecture, sort of a blueprint of how we're going to connect existing or new smart devices into an environment. And so one of the things we also utilized was the Intel IoT platform architecture for connecting the unconnected. And that was something that helped us identify where gaps were with regard to not only security, but the flow and the smooth ingestion of the data. And then I guess to sort of wrap in terms of we've now scaled to 4 stores for Levi's. And so now the other area that we're addressing is this notion of manageability. Now that we have these great devices, these IoT devices now connected, the notion that we want to address and manage is this notion of managing all these endpoints that are out there. So we used the Helix Device Cloud Manageability Service, which allows us, regardless of its of what type of device it is, and there's multiple, disparate types of devices, we're able to push down a very small agent to that device and be able to remotely not only manage it, but provision and even decommission it if we need to.
Okay, great. Thanks. Steve, Railway.
Yeah, so there were some similarities as well as some differences in the scaling factors for each of the 4 customers that I talked about in the first section. So in the first case, the safety system, consider that the country's largest railroad, Union Pacific, has 8,500 locomotives and over 32,000 miles of track. In their 2012 annual report, they said that they had 4,000 wayside signal detectors that generated 40 million data points a day. So that's about 10,000 data points per wayside device per day. So naturally, these 10,000 data points aren't going to be spread evenly throughout a 24-hour day. Rather, it's going to be bursty. It's only going to generate data when a train's in proximity. So there's going to be an IoT gateway device that's connected to an array of sensors, acoustic sensors, temperature sensors, RFID, and so on. And that gateway is going to receive multiple signals from multiple sensors, essentially all at once as the train's flying by. So needless to say, it's got to have the ability to ingest a sudden burst of data from many sensors all at once. And depending on, for example, the size of the rail yard, you're going to have different numbers of sensor devices connected to different gateways. So the gateways need to be able to handle whether it's 10 devices connected or 100 devices connected. The second customer's use case, which again was the customer that is developing supervisor and control systems on the train and moving that processing out from the server to the train itself, their scaling requirement isn't quite so dramatic because they are moving the data out from the cloud to the edge. In other words, they're moving that diagnostic function from the from the control center that were executed against batch uploaded data to the train to be executed in real time, and that data made available to operators immediately. They have some similar scaling requirements to the gateway that I just described for the safety system, but they have no scaling issues upstream since the control center will continue utilizing that batch system. And then the third customer, which was the scheduling application, has essentially the same scaling factors as the first, the safety-related system. So again, you've got gateway devices collecting input from wayside sensors and the centralized processing engine that aggregates data from the gateway devices. And then finally, the last customer doing the pull versus push messaging, they have scaling concerns only at the server or at the cloud level, since that system doesn't use a database system at the source or at the destination of the messages. It's only in the center. Carl?
Okay, great. Thanks so much, Steve. James, your thoughts on scaling factors?
Yeah, boy, it's hard coming after such a good group. A lot of it's been talked about. I mean, obviously, we all have our solutions around safety and security of the operating environment and things like that. But you also have to have a system that is able to scale both in the field and at the data center. And a lot of times people will overlook one end or the other. A lot of the use cases that we have, you have mobile assets or field assets that are connected via cellular, and you've got to control the data flow to and from those because under normal conditions you may have a temperature sensor that, for example, is reading 30 degrees, 30 degrees, 30 degrees, 31 degrees, 30 degrees, and there's no point there's not necessarily a point in moving all of the raw data, especially if it's lossy or lossy communication, or if it's a communication that has a cost to it. So you may want to once a minute aggregate 10 sensors together and send all of the values or send an average of the values and the max and the min, things like that. But you need to have the ability to react to that when you have a particular asset that goes out of normal bounds. So you have to have some edge analytics to be able, in our case, it would be our business rules product that is looking out on the edge on a gateway that's looking at this and determining what's normal and what's not normal. And then when you hit an abnormal condition, raising alerts, increasing verbosity of the data that's being sent, potentially even shutting down a generator or shutting down something based on the sensor data. For example, we have asset tracking applications where environmental conditions on that asset, temperature, vibration, things like that, can cause either in a minor alert the verbosity to go up, and you start alerting the driver, you start alerting the warehouse different things like that. Or, you have an audible alarm on the package itself, and you're also able to then mitigate through that, mitigate the insurance costs and things like that. But when you get to hundreds of thousands or millions of these, you have to be cognizant of the amount of data that you're shipping over the wire, because from a cost standpoint and a bandwidth standpoint, you whether it's asset tracking or predictive maintenance or whatever, you've got to minimize the footprint over the air for management, for regular telemetry and different things like that.
Okay, great. Thanks, James. Great topics 1 and 2. We've talked about use cases, examples, and scaling factors. Topic 3, we're going to drill down on what kinds of tools, techniques, and key components address these scaling needs of the system, and which scaling considerations do they address, and what was the end result. James, you were talking. Let's just kick it off with you.
Yeah, so to go further, you're basically going to need a microservices architecture of some sort where you have event-driven processing, right? So you're going to have all of these data points that are going through, and generally you're going to react to those events. So both out in the field at concentration points, at gateways and things like that, if the use case requires them, or in the cloud, you're going to have software that's able to ingest data, normalize it, route it to the right applications, and then be able to then act on that data, in a tactical fashion, but also to be able to route that data to long-term data stores as well for strategic analysis. So the ability to abstract these services from each other is really important. So the use of a lightweight ESB and other services to be able to create standardized services with standard APIs on them, so that you can develop each of the implementations separately, but as long as you maintain consistent APIs between them, you're going to be able to change, modify, evolve over time things like complex event processing and routing and those different things without affecting each function, as long as the APIs are standard and are extensible so that you can add additional functionality later. The problem is, if you do this in a monolithic fashion, you're not going to be able to scale horizontally. So the thing about a microservice architecture in the cloud is, for the ingestion layer, you're able to, if it's done right, you just spin up another instance of the ingestion software, like AMQR messaging product, and you scale that horizontally. If it's not engineered correctly, then you have to keep throwing larger and larger systems at it and trying to shard and federate data, and it becomes a real nightmare.
Okay, great. Thanks. Brett, your tools, techniques, and key components for scaling.
Sure. So GE, for their patient monitoring solution, they've chosen to use what's termed a layered data bus architecture. This is one of the main implementation patterns in the Industrial Internet Reference Architecture published by the Industrial Internet Consortium. They have at least 3 implementation patterns sketched out in there, and that's one of them. And GE, to implement the data bus fabric, as they call it, they're using RTI's implementation of the DDS standard. That's a data sharing standard for industrial IoT. So with the layered data bus architecture in DDS, they can scale from the 2 devices to the 200,000 devices that I've already talked about fairly easily. At each layer of the data bus, they can perform analytics locally to convert into information. They can do local data storage if need be, which is usually the case, as well as data filtering at the different levels of the architecture so they can meet their scaling and performance needs. So the data bus architecture begins, for example, within a single patient room. They'll have a data bus. And then at a layer above that, typically at a nursing station or maybe on the floor, they'll have a data bus that's sharing information between multiple rooms and the nursing station. Then often above that will be a data bus covering the entire hospital, integrating information across the hospital. And then another layer back at the back-end information center for the hospital chain, integrating analytics and storage and UIs. So each layer passes along a subset of the data that the next layer needs as it goes up. And each layer kind of monitors and enforces performance and the security needs at each level. So for security, they use DDS's data item by data item security model. So you can actually encrypt data as it flows as opposed to everything that's going on the network. And this way, it's much more straightforward for them to enforce the privacy rules for patients, as data is tagged by patient, and that can be encrypted and managed patient by patient, as well as guarding the system and the devices against cyber attacks. And instead of securing absolutely everything on the network, they can trade off security, by not encrypting non-critical data to gain performance. And they can also match a particular device to a particular patient, tag that data to the patient instead of device, and manage it all that way.
Great, thanks a lot. Josh.
Yeah, so this data streaming, kind of cloud-to-cloud connection that we've enabled here for the Owlet Baby Monitor solution, it's very much a traditional kind of DevOps server infrastructure monitoring use case, which is all fine, right? There's a lot of tools out there, but we needed to do more because part of what ALO's kind of culture is about is enabling our customers to be as self-sufficient and successful on their own as possible. So what we did is we built additional tools, right? So we built basically a diagnostics UI that really reported on the common elements of these data streaming connections that will basically inform if there's any issues or problems that either the Owlet team can address and or our own support team, right? So this is stuff like online and offline history. What's the status of these various buffers, right? Is something queuing up too large? We need to do something about it. But also being able to search on stream keys and see connection logs, right? Because again, this customer of ours has based their business around this cloud-to-cloud solution. And so we want to give them everything they need to be successful with that, right? And also develop their own baseline level of understanding. Now, those tools are also used internally, right? But we've extended them for our own use. So we added things like application heartbeats, right? So we can detect inactive connections. We can clean those up, right? We have our own diagnostics UI as well, but also just general hygiene, right? Cleaning up old or dead connections, cleaning up inactive stream keys, right? And so basically to maintain some sanity of the connection so that we can better support and monitor it. Now for techniques, it's not real rocket science, but it's more of, I think, diligence to make this customer successful by creating a really powerful and good tool. So we have great cloud architects being in the Silicon Valley. We're blessed with that, right? So they have some really neat usage of queuing and allowing buffers to scale with spikes in data. That's great. But we also have kind of this no data loss policy in quotes, right? Which is, look, we're constantly testing and iterating on this stuff. We have the data transmitting to us. That's all fine. We have that down. But when we're connecting to another cloud, right, there are issues there. There are little inconsistencies. And so we're constantly testing, constantly iterating on this process so that we can minimize and hopefully, knock on wood, eliminate data loss. We'll see if we can get there, right? But also, how do we spin up resources? As, again, back to the idea that some superstar tweets about the Owlet Baby Socket giant spike, how do we scale out and enable that?
Great, thanks. Bridget, you talked a lot about the RFID gateway and security issues and then the cloud stuff that Intel kind of has spectrum of solutions. Can you just take a minute to summarize the tools and techniques for those?
Sure. So remember, we were trying to help Levi's address their real-time inventory accuracy challenge, as well as position them as a responsive retail store. So the tools we use cover 4 basic areas. First, we use the Intel IoT platform end-to-end architecture, or blueprint, if you will, that literally explains how you connect from sensors to things at the edge, ingest that data, move it through the network securely and into the cloud for analytics. We used a variety of Intel technology components, starting with the Intel RFID sensor platform that basically serves as a sensor aggregation hub for data coming off the RFID tags and other types of sensors. We use the Intel IoT gateway that comes pre-integrated with the Linux OS, integrated McAfee for security, as well as an agent that would allow us to remote manageability of all the different endpoints that are connected, as well as allow us to ingest and normalize the data. And then we also, what I didn't mention is we used Intel's trusted analytics platform we call TAP, which is an open source big data analytics platform that is where we basically the destination for the data for the big analytics. And together with that, we essentially, created this, edge to cloud secure real-time inventory management environment, and we set them up for with an updated infrastructure so that Levi's can build on that for additional applications and expansion.
Great, thanks, Bridget. That's from RFID to cloud. That's lots of tools and solutions in there. Steve, let's talk about tools and techniques and components for scaling in your applications.
Sure, Kurt. So you touched on a lot of different topics there: security, encryption, over-the-air upgrades. But for a database, the thing I'm going to focus on is fast concurrent access to the database, particularly for ingest. And I'm not going to talk about scaling factors for big data and analytics in the cloud because, frankly, we could do an entire presentation just on that topic alone. So for a database system at the edge or on a gateway device, we're probably talking about a typical embedded database system. And the critical scaling factor is going to be the database system's ability to keep up with that incoming stream of sensor data. For example, a gateway should be able to ingest a few sensor data streams or quite a few sensor data streams, as I alluded to in the last segment. So this, in turn, is going to be a function, or handling this is going to be a function of database design, database features, and application design. So with respect to the database design, you're going to want to minimize the indexes or use something like hash indexes that don't have O-log and complexity. Various tree index implementations, B-tree variants, they have to be continually rebalanced, and that's just going to chew up CPU cycles and time. So you want to try to avoid that. With respect to database features, the requirement to ingest sensor data from a lot of connected sensors implies concurrent writes from multiple threads or multiple processes. So the database system has to be able to support that. Now, SQLite, for example, controls concurrency at the database level. That means that only a single task can write to the database at any moment in time. Other tasks are going to be blocked, likely sitting in the kernel's waiting queue, so they're not consuming CPU cycles because they're in the waiting queue, but they're not executing either. Other database systems support concurrency through pessimistic table or row level locking. The lower the granularity, the better, but pessimistic locking below the database level requires message passing between the client applications and a lock arbiter, and that's going to result in unpredictable latency. An optimistic model is better. It doesn't require any locks, therefore it doesn't require an arbiter, it doesn't require any message passing, and with proper design, it shouldn't introduce any conflicts. And then lastly, with respect to application design, if the database system isn't going to be capable of keeping up with the sensor data stream, then it's going to be necessary to write your own buffering solution. In other words, queue that data up in your own buffer and then write from that buffer to the database system as fast as the database system can support it. That approach is going to work well for systems like the first and the third that I described, where you have rail wayside data collection systems that are bursty in nature. That buffer can expand dynamically during a burst of traffic and then contract when the buffer is emptied out to the database during more quiescent periods. Back to you, Kurt.
Great, thanks a lot. We are now to the Q&A. We don't have a lot of time for the Q&A, but I do want to touch on one question. There's a great question from an audience member that talked about the percentage of traffic kind of to expect for these applications between the devices and sensors themselves, between the devices and the gateways, between the gateways delivering information to the cloud or fog, and then the percentage of traffic among the servers and databases within that. Let's start with James. James, do you have a comment on, you might be on mute, on like the percentage of traffic to kind of expect for your application?
Sorry, yeah, I was talking to mute. Well, it's definitely going to be more than you can ever anticipate, right? You're going to find new ways to use data. You're going to find that you're going to have more data than you ever contemplated. And the way that, the biggest problem is going to be suffering under the deluge of data that is out there. So, you've got to make sure that you're bringing back only what you really need and what is going to provide value with the ability to access and increase the amount of data when you need it.
Right. Okay.
So, yeah. So I mean, it's really, really important that you have a really good data model, that not only the data types of classes of data that you're going to have, but how you have to secure it, what the life cycle of it is, how long it's valid, how long it should persist through the system, where it needs to be used, and you need to have that classification for everything.
Okay. Brett, do you have an idea of kind of the percentages of traffic to expect or ratios between those components in the IoT?
Unfortunately, the answer really, it depends, depending on the use cases and how the system is structured. But in the GE case, the data is actually, and the data that's flowing is actually pretty evenly distributed across all those layers, because they're working with different kind of levels of granularity of data.
Okay.
More real time down below and less latency up above.
Yeah,
okay.
this is
Bridget.
Yeah, the only thing I would add to that is I think I would first of all echo it really does depend on the use case. This is very use case driven in terms of how real time need do you have for the data, like autonomous driving, right, where you need sub-millisecond response and that sort of thing. But I think what we're seeing is that there is a shift for IoT-generated data. We're expecting 40% of that data to be computed and processed at the edge by 2018. So as most of our early deployments are sending a lot of the data to the cloud for analytics, as the edge gets more intelligent and more capable with compute, we're seeing that shift now, going to start to sway over to most of that data distribution is going to be handled at the edge, and only filtered data would go into the cloud.
Okay, great. Stephen, do you have any kind of information on ratio of traffic or mostly within the database environment?
Yeah, so with respect to these railway systems that I've been talking about, you really can't talk about ratios or percentages. I mean, all of the sensor data being collected by the sensors going into the gateway, and maybe not all the data is going from the gateway up to the cloud. For example, if there was nothing unusual, then it's probably going to get aggregated and sent up in some aggregated manner. But anything that's out of bounds is going to generate an immediate event. For example, there's a stuck brake, so that leads to a high temperature reading. Well, that's something you want to know about right away. You don't want to wait until some time where things are aggregated.
Yep. And Josh, what type of IoT device events can the customer's data stream client subscribe to for your infant application? Just for 15 seconds here.
Yeah, we have various subscriptions, so it kind of actually talks to the edge, whereby these devices are kicking off various types of data. And so you can subscribe to data points, data point acknowledgments, meaning the device took some command and was responded, location changes, registration events, and connectivity, but also our edge service factors into that. So you can filter out various events on the edge and only really push up to the cloud the data that you're really interested in.
Got it. Thanks. That brings us to the conclusion today. I want to thank our panelists for sharing your insights on scaling IoT. We at Open Systems Media, Ayla, Intel, McObject, Red Hat, RTI want to thank you, the audience, for attending and contributing those excellent questions. This eCast will be posted online at the URL shown on your screen in 24 hours, and an audio-only podcast version will also be made available there. Open Systems Media events are copyrighted and may not be recorded or without the express written consent of Open Systems Media. Thanks for attending today, and have a great day.